Good morning. I'm Stephen Hurrell, and I'm going to briefly explain how we can use light structural dynamics to calculate ancient gravity. These results indicate that ancient life lived on a reduced gravity Earth and also supports the geological evidence for an increasing mass expanding Earth. My initial thoughts about ancient life's gravity began in 1987. Dinosaurs have been a source of wonder and fascination since they were first discovered, and a large part of this fascination is their gigantic size. They were the largest land animals ever to live, with most average-sized dinosaurs dwarfing the largest land animals of today. This large size naturally leads to the obvious question: why were the dinosaurs so big? Here's the Berlin Brachiosaurus. You can see me standing in front of its skeleton, and this gives an impression of the scale of this immense creature. The neck bones of a smaller dinosaur, Diplodocus, can also be seen on the right of the photograph. Here's the skeleton and outline of Diplodocus and the Indian elephant, both drawn to the same scale. Diplodocus stood 3.8 meters tall at the hips. The Indian elephant is only 3.1 meters head height. Carnivorous dinosaurs, such as Tyrannosaurus rex, were also gigantic. They were comparable with elephants in size, but seem to have led a much more active lifestyle than any elephant. The gigantic size of dinosaurs is obvious, but why were the dinosaurs so huge? Why don't present-day animals grow to the immense proportions of the dinosaurs? Scale effects provide part of the answer. Consider these two boxes. A seemingly simple question is, how much bigger is the larger box than the smaller one? But consider the question in more detail. If the boxes are measured by the length of their sides, their linear dimensions, the larger box is twice the scale of the smaller box. The area of the larger box is 4 times the scale of the smaller box. The volume of this larger box is 8 times the scale of the smaller one. As any object increases in size, its volume increases quicker than its area, and its area increases quicker than its length. It is this mathematical relationship between length, area and volume which limits the maximum scale of life. Here is a standard 4-legged animal in 2 sizes, small and large, with the weight of each animal supported on its 4 legs. Just like the simple box, the linear dimensions, height, width and breadth, of the large-scale animal are twice those of the small animal. The volume and weight of the large animal is 8 times the small animal, but the legs of the large animal are only 4 times the area and strength of the small animal. The large animal's leg stress is twice the small animal's leg stress because the weight of the large animal has increased quicker than its strength due to the scale effect. This simple example clearly explains why all animals must be limited in size. This scale effect is well known. The Royal Institute Christmas lectures are televised each year in Britain, and the 2010 lectures gave an interesting series on why size matters, with models of 2 scale animals. One was twice the size of the smaller animal. Although his model animals are round, it demonstrates the same scale effect on life we have just looked at. The small animal can stand on its legs, but what will happen to the larger animal? The legs collapse because of the scale effect. This series of Royal Institute lectures on scale effects are well worth watching and are still available on their website. We can see the scale effect limiting the size of real life. The legs of large-scale animals generally tend to be proportionally thicker for greater strength. Here's the thigh bone of a deer, a rhinoceros and an elephant. The small solid shapes indicate the true relative size of these bones. the larger outline indicates the difference in their shape. The deer, on the left, has the most slender legs, the rhinoceros relatively thicker, and the elephant has great, thick, sturdy bones to support its massive bulk. Plants are also affected by their scale. Small flowers rely on the hydrostatic pressure of water within their cells for rigidity. By blowing out their cells with water, they form solid structures that can stand erect. The hydrostatic pressure system is adequate to maintain the rigidity of small plants, but as plants grow larger, their weight increases faster than their structural strength. To cope with the greater stress, larger plants have developed special high-strength tissue we know as wood. The wood fibers of a plant have the sole function of keeping the plant rigid. What limits the scale of today's life? The factor which limits the scale of today's life is a combination of these scale effects and gravity. It is gravity which gives all animals weight and so limits their maximum size. But what happens in a reduced gravity? Here are our standard animals once again. The two animals are exactly the same shape, and the larger one is twice the linear scale of the smaller animal. But the larger animal is now in a reduced gravity of 1/2. So the larger animal would only be 4 times as heavy as the smaller one. Both animals have the same leg stress because of this difference in gravity. We have effectively shifted the relative scale of life towards a larger size by placing it in a reduced gravity. For a particular form of life, the linear scale of land-based life is inversely proportional to the strength of the gravitational field. This can be represented in a formula where SR is the scale of land-based life relative to today's land-based life, and GR is gravity relative to today's gravity. Today, there is a whole range of life limited in scale because they live in our present gravity. If gravity was half its present value, then the relative scale of life would be twice its present size. If gravity was less on the ancient Earth, we would expect life to be larger, and this is exactly what we see. A lower gravitational field would allow the scale of all land-based life to become larger, and this illustrates how the immense size of the largest dinosaurs would have been a natural result of a reduced surface gravity on the ancient Earth. The force of ancient gravity can be estimated from ancient life using a number of different methods, including the relative scale of ancient life compared to present-day life, ancient life's bone strength, its muscle strength, ligament strength, and its blood pressure. In the upper Carnivorous, 340 to 280 million years ago, numerous giants existed. Ancient dragonflies were much larger than any present-day species, possibly up to 76 centimeters across the wingspan. A life-size reconstruction of a giant dragonfly by Werner Krauss clearly demonstrates the impressive scale of this ancient creature. Fossils of giant horsetail plants are much larger than their present relatives. One of the largest known invertebrates was a giant millipede, which is reconstructed here as a life-size model. Dinosaurs' muscles and flesh have hardly ever been fossilized, but the forces in the neck ligaments of at least one of the sauropods, Diplodocus, from the upper Jurassic of about 150 million years ago, can be calculated from the shape of the bones which held the ligament. The neck bones of these dinosaurs are V-shaped to contain the ligament, helping to raise and lower their heads. By calculating the force that this neck ligament was likely to exert, and by estimating the volume of the neck and head, it is possible to estimate the force of gravity when these animals were alive. Dynamically similar life can be compared. Triceratops was similar in appearance to a present-day rhinoceros, with the most noticeable difference being that Triceratops had 3 massive horns on its head and it was much larger. Triceratops grew to 8 meters in length and its mass was about 9 tons. so it was similar to an elephant in mass. Despite its elephantine size, the Triceratops seems to be dynamically similar to a present-day white rhinoceros and should have galloped in a similar manner. It is difficult to explain how such a large animal was so athletic unless gravity was lower. The general trend of scale reduction is noticeable from the observation of giants of the past. After the dinosaurs became extinct, a range of supergiant mammals reached the size of smaller dinosaurs about 40 million years ago. These have all been replaced by the smaller animals of today. This trend can be seen more readily by plotting the relative sizes of giants of ancient times compared to modern life forms. 350 million years ago, the scale of life was between 3 to 5 times greater than similar forms of life reached today. By the time of the first dinosaurs, this had reduced between 3 to 2 times, and at the end of the dinosaurs' reign, it was 1.5 to 2 times the scale of present-day life. The low gravitational field on the ancient Earth can be estimated from the relative scale of ancient life. This graph indicates the probable change in gravity on a reduced gravity Earth, based on ancient life. We can see that surface gravity has been slowly increasing over hundreds of millions of years. But why would the force of gravity have changed? There is one obvious fact about celestial bodies like the Earth. Surface gravity is proportional to size and mass. The Moon has a low surface gravity to match its small size. Amongst the planets, Mars is smaller than the Earth and has a lower gravity. Venus approaches both the Earth's diameter and gravity. There is a definite relationship between the size of a planet and its surface gravity. Based on the relative scale of ancient life, when the dinosaurs roamed the Earth, it was about 1/2 the diameter it is now. Since that time, the Earth has increased in its diameter, mass and surface gravity, reducing the relative size of life as gravity increased. This ancient reduced gravity Earth is remarkably similar to the geological evidence for an expanding Earth. The geological evidence indicates that the present-day continents were once joined to form one large continent, but as the Earth increased in size, the continents began to split as new ocean floor filled the gap. These are my own reconstructions I produced in the early 1990s, but they are remarkably similar to other reconstructions we have seen at this conference. These expanding Earth reconstructions, based on geological evidence, can be used to estimate the size of the Earth in the past. Assuming that the Earth has increased in mass to produce the expansion indicates that gravity has increased over time. This is an increasing mass expanding Earth. The variation in gravity was predicted from the scale of ancient life, and the variation in gravity predicted from an increasing mass expanding Earth is comparable with this gravity variation. There are therefore two completely independent lines of reasoning which indicate that the Earth has expanded in size and mass to increase its gravity. All these concepts are covered in much more detail in my book Dinosaurs and the Expanding Earth, which is now widely available as a 3rd edition. Thank you for listening.
I actually have 2 questions. One about the chart in your book where the Allosaurus is, you give a calculated relative gravity that's less than for the